Okay, so I was working on an NMR problem with the student, and we came across a question that I thought was relevant and worth sharing because I don't think there are many tutorials out there about how to actually solve certain types of problems like this. As you see on the left, we have a proton NMR spectrum, and the structure that it happens to correspond to I drew in here. The first part of the spectrum is pretty easy. Things that don't generally need a ton of explanation once you've had a bit of introduction to NMR. We see here on the right that we've got a quartet. That's pretty obvious. We see in the middle at 4.5, we have a triplet. That's pretty obvious. We see at 6, we have a doublet. That's pretty obvious. But at 7, we've got something more complicated. And often when you see something like this, you might, say, well, I'll leave that and try to figure it out later by process of elimination, or I'll use other information to try to figure out what the structure is, and then we'll just attribute that to a particular aspect. This is the result of complex splitting, and I know that many lectures cover how complex splitting works. Just to show that, on the top, this figure 1, we have the normal types of splitting. Singlet, which is no splitting, but then we have a doublet, a triplet, a quartet, a heptet, and we're going to use these numbers in a minute. The number of neighbors, or the number of interactions that are causing that signal. So a singlet means there are no neighbors. So that proton is not being affected by anything else. So it shows up as just a single peak. But if there's one neighbor, that proton is being affected by its neighbor, and so it shows up as a doublet. Or if you have 2 neighbors, 2 interactions, it shows up as a triplet, or 3 interactions, it shows up as a quartet. Extrapolating on this pattern, if we had a heptet, that would mean that there are 6 neighbors. This is the n+1 rule, right? That if you have 0 neighbors, you have 1 peak. If you have 1 neighbor, you have 2 peaks. The doublet, if you have 6 peaks, you'd have 6 neighbors, you'd have a heptet, 7 peaks. So that's normal splitting. But the complex peaks, some of them are more obvious. For example, the doublet of doublets is, you can see why that would be considered a doublet of doublets. Maybe you can see the doublet of a doublet of triplets somewhere, or maybe recognize a doublet of quartets. But you see, even most guides or textbooks, they say, well, if it's more complicated, we're just going to call it a multiplet, and we're kind of going to wave our hands and figure it out later. And I wanted to help my student actually understand what that is and how to solve for it. Okay, because sometimes you just have to solve for it. Sometimes spectra are really complicated, and it's just something you have to deal with. There's no way around it. So I'll illustrate on this molecule where we are getting these signals, and then we'll practice kind of decoding that more complicated signal. So let's start with our quartet. A quartet, again, means that we have 3 neighbors, right? So we are looking for a proton that has 3 neighbors. So there are 2 protons that are equivalent, and they both have 3 neighbors. Those are these protons right here. Now, what are their neighbors? Their neighbors are the 2 here and the 1 here. Now, this is a quartet because the relationship, the splitting constant from the red to the blue is 7 hertz. And the splitting constant from the red to the green is 7 hertz. 7 hertz. And since those relationships are the same, blue to red is the same as blue to green, those neighbors kind of appear in the same signal. And so the reds appear as a quartet. Right? We can look at the triplet. So we're looking for the triplet, we're looking for hydrogens that are next to 2. Okay, because 2 signals, 2 neighbors, causes a triplet. And that's the blues now, right? Because the blues have 2 neighbors, the 2 reds. Now, obviously, since the reds are equivalent, the relationship to both of the reds from the blues is the same. So the blues would be a triplet. Let me color code these. And again, this is not new. This is not difficult. This is something that you have to master if you just do basic NMR. But we're going to refer to these ideas when we try to decode this multiplet on the left side. So we've got the red hydrogens are causing a quartet. The blues are causing a triplet. All right, where's the doublet? So a doublet would have 1 neighbor. So we're looking for a proton with only 1 neighbor, and that would be the pink proton right here. He has 1 neighbor, which is the green. So let's make the doublet the pink. Okay. Now, if you know the structure, you can explain the multiplet. At least you can rationalize it away. It turns out that the relationship of the green to the red is not the same as the relationship from the green to the pink. Okay, the coupling constant, like we said before, from the green to the red is the same as red to green. That is 7 hertz. Okay, no problem. But the relationship from the green to the pink, that coupling constant is about 12. So that means that it doesn't show up as a normal triplet. Okay, or excuse me, it doesn't show as a normal quartet. You'd expect the green to couple with the reds to make a triplet. You'd expect the green to couple with the pink to make a doublet, and those would both be different, but they're inherently interacting. Green feels red and green feels pink. So this we could conclude just based on the structure. We have a doublet and a triplet. The doublet is the larger coupling constant. So we would call this a doublet of triplets. Okay, a doublet of triplets. That's how complex splitting works. And again, that happens when you have different relationships to your neighbors. The green's relationship to pink is different than green's relationship to red. Right? That wasn't the case for red, remember. Red had the same relationship. 7 hertz from red to blue and 7 hertz from red to green. So they all counted together, and we just called it a quartet. It was just a normal quartet. So yes, based on the structure, we can say, okay, that's a doublet of triplets. That's obviously that signal is being caused by the green proton. But what if it wasn't so obvious? Okay, what if you didn't know your structure? And therefore, how could you know any other way that was a doublet of triplets? Now, if you look really close, you might say, oh, that definitely looks like 2 triplets that are kind of the result of an existing doublet. So there's a doublet first, and then that doublet splits into its own triplets. And you can maybe see, okay, that's what that looks like. But let me show you an example where it's not obvious what we have. For example, this. Okay, this is a very complicated multiplet, and without a lot of experience, you might not be able to see what it is. Is that a doublet of doublets of doublets? Is it a doublet of triplets of doublets? Is it what is it? It's hard to know without prior experience, having seen these a lot or having studied what these shapes tend to look like. Fortunately, there is a way to decode it. Okay, there's a systematic way to approach this, and I'm going to walk you through that. How to do that. So in the event that you are doing NMR and you get a multiplet like this and you go, oh my goodness, how am I ever going to figure out what the heck is going on here? This is how you do it. Okay, now, anytime that you have a multiplet, I think it's really important that you have the actual data associated with those peaks. And most NMR programs will provide this right on the spectrum. Sometimes you can hide the numbers if you don't want to see them. But these numbers, if the spectrometer is picking up these frequencies, it can print them out for you. So this is an example of what that output might look like. We have the ppm, so the actual chemical shift. We have the frequency, the raw frequency, okay, not just independent of anything. Remember, ppm is always relative to TMS, but these frequencies are the raw frequencies. And then the height, the integration of these peaks. So if we have this raw data, and in fact, I'll show you, you only really need the frequencies. The heights help. Sometimes you can kind of qualitatively assign the heights. The heights help to have, but all you really need is the frequencies, the hertz. All right, so the first thing I would do is, the first step here is to normalize the heights. Remember these integrations, the height is the integration, which means that a 1 means that it's 1 proton causing that signal. A 2 means that it's 2 protons causing that signal. A 3 would mean that it's 3, or some ratio thereof. Okay, 1 could mean 2 protons, and then 2 would mean 4 protons, for example. It's a ratio. But what I like to do is normalize them. So what I'll do is take all these heights and just divide them all by the smallest height. So to normalize this set, what I did here is I took all of the heights, and we're going to use this table going forward, and I just divided everything by 1.06. And so this is what we get. We get 1, 1.16, 2.05, 2.13, okay? The numbers get really close to being 1s and 2s, and so I just round them. Okay, in this case, we rounded down for everything. So we have the 2486 is a 1, the 2490 is a 1, the 2492 is a 2, etc. And you can see those heights are roughly visible here. We've got the smaller peaks and we've got the taller peaks. So those are the 1s and the 2s for their integration. All right, so here's what we're going to do. We're going to start at the top of the table and work our way down. Essentially, we're going to start at one end of the multiplet and work our way to the other end of the multiplet. And what we should do first is look at the first relationship, okay, the first pair. So we have a height of 1 and a height of 1, and their separation is 4 hertz, okay? Now, what is a 1-to-1 relationship? I mean, what does that mean? It means it's a doublet, right? Going back and looking at our picture of our signals, a doublet is a 1-to-1 ratio. Okay, it's 2 equal peaks. Okay, a doublet is just 2 equal peaks, 1-to-1 ratio. So since our first pair here is a 1-to-1 pair with a separation of 4, okay, we are going to look for all doublets with a coupling constant of 4. Okay. And we're just going to go through and note what those are for the moment. So first, okay, so we have a 1-to-1 at 4. Here we have a 2-to-2 at 4. Okay. Here we have another 2-to-2 at 4. Another 2-to-2 at 4. And another 1-to-1 at 4. So all of those are doublets with a separation, a splitting constant of 4. Okay. None of these other relationships are doublets of 4s. For example, this pair here, the 2490 to 2492, that's a 1-to-2. And the separation is 2. So we're not looking for that. Okay, we're looking for doublets of 4 because that's what our outermost pair tells us to look for. So another thing to realize with a doublet is that the 2 peaks of the doublet are centered around a center point. So if we were to kind of zoom in, let's zoom in on our pink doublet over here. Okay. So one of these peaks has one frequency, the other peak has another frequency, and the center of that is immediately in between. So we've got a center with the two peaks around it. And it's the center frequency that we care about when we're trying to decode these things. So let's go through and look at each of these doublets and find the center point. Again, we're going to note what that center point is. So for our first pair of doublets, or our first doublet, I should say, these are centered at 2488, right? Immediately between, exactly between 2486 and 2490. So we're going to say that's centered at 2488. Our next doublet, these guys, are centered at 2494. Okay. Our next guys were centered at 2500. Our next set is centered at 2506. And our last set is centered at 2512. Okay, so again, what we've done here is we've taken all of our signals, and because the first pair of signals represent a doublet with a separation of 4, we're going to kind of remove all of that splitting. We're going to unform that set of doublets. So we've taken the 2486 and the 2490 and we've returned them to one signal. That 2488 is kind of the unsplit signal of the 2486 and the 2490. Okay? So that's our first step, and what this tells us is that somewhere in this multiplet, there is a doublet of 4. Okay, a doublet with a separation, a splitting constant of 4. Now that we've done that, let's keep going. We're going to keep going until we've disentangled all of these signals. Now, we're going to, just like we did before, start with the leftmost signals. So now what do we have? Well, it's important to keep track of these numbers, which ones were 1s and which ones were 2s. For example, the 2488, that came from a pair of 1s. But the 2494 came from a pair of 2s. Okay, they were doublets of 1s and doublets of 2s. So now when we look at our next signals, our first pair is a 1 to 2. Okay. The 2488 is a height of 1, and the 2494 is a height of 2. So what signal type has a 1 to 2 ratio? That's a triplet. If we go back and look at our regular triplet, the height of the triplet peaks are 1 to 2 to 1. Okay. So since that is a 1 to 2, that tells us that we're looking for a triplet. And what's the separation? Okay. The separation is 6. Okay, 2488 to 2494. So we're now going to look for all triplets with a separation of 6. Okay. And here again, it's a little bit tricky, but this is how it works. So notice that we have 2488, which is 1, 2494, which is 2, and that's 6, right? That's a separation of 6. And then we have 2494 to 2500, and that's a separation of 6. Then we have 2500 to 2506, and that's 6, and 2506 to 2512, and that's 6. Okay. Well, these are 2s, and these are 2s, and these are 1s. Okay. So we're looking for triplets, though. We're looking for 1 to 2 to 1. So if we look at it like this, 1 to 2 like that, but then also 1 to 2 like that, what we end up with is that this center 2, this 2 in the middle, is participating in each of the triplets. It's part of the top 3 signals, but it's also part of the bottom 3 signals. So it's really 2 signals that are overlapping. So rather than it being a 2, let's think of it as it being a 1. It's a 1, which gives us our first triplet, 1 to 2 to 1. And then it's also a 1 part of our second triplet, 1 to 2 to 1. So the reason it appears as a 2 is that it's 2 signals overlapping. It's 2 1s overlapping. Okay, so we can see the 2 triplets here. You have to look carefully, and you kind of have to be very familiar with what you're doing. But we have to look for a triplet, right? Our first pair was 1 to 2, which only shows up in a triplet. So the only way we can get triplets out of this is if that middle number is shared between 2 of them, thus making it 2 overlapping 1s. All right, so the center point of a triplet is the middle signal. Okay, a triplet is centered around the center signal. Again, we can go back and look at what a triplet looks like, and you can see that the center of the triplet is centered right on that center signal. Okay, so this, well, again, like we did before, we're going to take the midpoint of that signal, of those signals. So the top triplet, and I'll change color here again. I'll do purple. The top triplet is centered on 2494. Okay. And the second triplet was centered on 2506. Okay. So these were 1s basically. Okay. So you can think of the one came down here, so that was from a 1, and this was from a 1. Okay. Regardless, we have 2 signals. Okay. That's clearly a doublet. Okay. The only way you could have 2 signals is in a doublet. And what's their separation? Their separation is 12. Right. So the midpoint here is 2500. But we've got a doublet of 12. So we've taken our 10 original signals. There are 10 signals here. The first thing we found was a doublet of 4. And so we removed that doublet of 4. When we removed the doublet of 4, we ended up with, instead of 10 signals, they all combined down into 5. Okay, we unsplit them back into 5 signals. Okay, those 5 signals we saw were 2 overlapping triplets with a separation of 6. So we took that triplet of 6 and we unsplit them. We found the midpoint of those and unsplit them. And then what we were left with is 2 equal signals with a separation of 12. So that's a doublet of 12. That's centered at 2500. So the center of our signal, okay, this point here, right through the center of our signal, that is at 2500 hertz. And to understand how we get the signal, we take that 2500 hertz center, that one signal at 2500, it's split into a doublet that's separated by 12. Those 2 signals from the doublet are subsequently split into their own triplets. So the 2494 is split into a triplet centered at 2494. The 2506 is split into a triplet centered at 2506. And the separation between those triplets is 6. And it turns out that we get that one peak that's overlapping with both, which is why it shows up as a 1, but we can understand that it's actually a 2. Sorry, it shows up as a 2. But we can actually understand that it's a single signal of 1 that is overlapping with 2 different splittings. So it shows up as a 2. And then we can split those triplet signals into subsequent doublets. So each of those 5 signals splits into doublets that are separated by 4. So this, or you always read it from the highest splitting constant to the lowest splitting constant. This is a doublet of triplets of doublets. A doublet of 12, that's then split into a triplet of 6, that's then split into a doublet of 4. And when I say doublet of 12, I mean a doublet where the peaks are separated by 12 hertz, or a triplet where the peaks are separated by 6 hertz. Okay. Now, there's a little shortcut that you can take to either help you confirm your answer or help you do a little bit of process of elimination before you start. So here's a trick, is you add up the integrations. Once you've normalized them and rounded them, add up the integrations. And this is 16. These integrations add up to 16. Now, what we want to know is, what is n if 2 to the n equals 16? Well, of course, n is 4. What does that tell you? That tells you that there are 4 interactions. Okay, so back here where we looked at, okay, the number of neighbors, or we called them the number of interactions, that number 4 is the sum of whatever we have. So if you know that you have 4 interactions, what combinations could that be? Well, remember, a doublet is 1 interaction, a triplet is 2 interactions, a quartet is 3 interactions. So 4 interactions, you could have a doublet of doublets of doublets of doublets. You could have a doublet split to a doublet, which splits to another doublet, which splits to another doublet. That would be 4 interactions because each doublet is 1. You could have a doublet and a triplet and a doublet, or some combination thereof. Okay, a doublet of doublets of triplets and a double of triplets of doublets, or a triplet of doublets of doublets. They're all 4 signals. So some combination of 2 doublets and a triplet, that would also give you 4 interactions. You could have a doublet and a quartet, or so a doublet of quartets or a quartet of doublets, where the doublet gives you 1 interaction and the quartet gives you 3. That makes 4. Or you could have a triplet of triplets, where each triplet is 2 interactions. So these, I think that's it. I believe that's it. But those are the 4 types of multiplets that would involve 4 interactions. So if you did this first, if the first thing you did was add up all of your integrations and then figured out what 2 to the n was, then you say, okay, my answer must be one of these 4 choices, or some permutation. Or you can use it after the fact and you say, okay, I need 4 interactions. Does my answer correlate to that? Indeed, it does. This is indeed a doublet of triplets of doublets, which would be 4 interactions. Okay. All right, so that's how you do this. We're going to do one more example, but once you can solve one of these, I think you can understand, or I think you can see that we did this in a pretty formulaic way. Okay. Once again, let me review. We looked at our first signals, the first 2 in our list, and we recognize that those are a 1-to-1 signal pair, 1-to-1, which means we're looking for a doublet. There is a doublet in here, and the doublet is 4 hertz. That's the separation. So then we went through and we found all of the doublets, 1-to-1 or 2-to-2 or 3-to-3, 4-to-4. They're all doublets. They'd all be doublets. We found all the doublets that were separated by 4, and we unsplit them. That gave us 5 signals. Okay. We then saw that those 5 signals were 1 to 2-to-1. And that would be a triplet. And the separation was 6. So we looked for all the triplets that were separated by 6, and we unsplit those. Take the center of those triplets and resolve them back down to 1 signal. And then we had 2, the 2494 and the 2506. Those were 2 signals, so obviously it's a doublet. And the separation is 12. And so we unsplit that doublet, and we got our center of our signal at 2500. So we had a doublet of 12, a triplet of 6, and then a doublet of 4. All right, and those interactions are 4 interactions, which corresponds to our integration. So this is often how this is visualized. This is from a multiplet simulator. I don't have the link here, but you can, if you Google multiplet simulator, I think it's probably the first result on Google. And you can put in your, oops, this is out of order. I don't know how that happened. But you can put in your multiplicity. You can put in the types of signals that you have, and it will generate the multiplet for you, which is really cool because you can play around with different combinations of doublets, triplets, and quartets. You can play around with their coupling constants, and you can see what different kind of shapes you can get. But this is the multiplet that we were just looking at. It's a little bit, the peaks are a little bit more nicely separated than in the actual spectrum. But nevertheless, this is the same type of signal. You see on the left, it's a doublet of 12, it's a triplet of 6, and then a doublet of 4. And you can see in that branching tree at the top, our red signal was our center signal. That was the 2500 that we ultimately ended up at. The green signal is that doublet of 12. Those green signals are subsequently split into triplets, the blues, and those are separated by 6. And notice that the 2 triplets overlap. So in the blue, this is a 1 to 2 to 1, and this is a 1 to 2 to 1. And so that shows up as a 2. That's why we saw it as a 2 in our integrations, but it's overlapping with both triplets. So we have triplets there, and then those triplets are subsequently split into the smaller doublets, which are the doublets of 4. And that's how we get our signal. All right, so let's do another example. Go back here. All right, so another one, a little bit more complicated. We've got more signals, but we're going to approach this the exact same way. We've got our ppm, our hertz, our heights, our integrations, and we're going to do the exact same thing. Now, in this case, all of the hertz are at 0.5, and I just ignore that. It'll fix it. It'll resolve itself. But so that's what I did down here. I just took our hertz that I just made 2482. I just made that 24, and 2484 0.5. I just made that 2484. So I took our hertz, took our signals and our heights, and I normalized them again. So the 1.11 is the smallest height. So I divided everything by 1.11. And when I get that, what we clearly see is we've got things that are closer to 1, and we got things that are closer to 2. We've got a couple 1.99s there. So then I rounded everything, and we get to our general integrations. And again, you can see those integrations here. We've got a bunch of peaks that are smaller, that are like half the size of others. We've got 2 that are very tall, that are double everything else. So the tall ones are the 2s, and the small ones are the 1s. Okay. So let's do our little shortcut first this time, because that's going to tell us again what we can expect from our answer. If we add these up, we get 16 again. So that means that 2 to the n is 16, and therefore n is 4. So we actually have the same choices that we had in our last problem. We could have a doublet of doublets of doublets of doublets. That's 4 interactions. We could have some combination of doublet, triplet, doublet. So doublet of triplets of doublets, or doublet of doublets of triplets, or triplet of doublets of doublets. Those would all be 4. We could have the doublet, a doublet and a quartet. Some combination, either a doublet of quartets or a quartet of doublets. That would be 4. Or we could have a triplet of triplets. And that would be 4. Each triplet is 2. And again, maybe if you're really experienced, you can look at this and you could predict what's going on here. But maybe not, probably not. Certainly not a first-year organic student would not be able to, see this pattern and go, oh yeah, that's a doublet of quartets or whatever. It's really complicated. So let's approach this more systematically. Let's not do any guesswork here. So just like last time, we're going to start at the top of the list. And we're going to say, what is our first interaction? So our first interaction is a 1-to-1, which is a doublet. And the separation is 2. So let's go through and find all of our doublets that are separated by 2 and find their midpoint, kind of unsplit those doublets, right? So that's a doublet. Let me just mark, we'll just mark them first because that's going to help. So that's a doublet. Now, if you look at the signals, we have a 1 to 2. And you say, well, that's not a doublet, right? A 1 to 2 would be a triplet. But if you look more carefully, the 2490 to 2492, and then we also have a 2492 to a 2494. So if we're looking for doublets of 2, you can see that those are really 2 doublets, and they share the 2492 signal. So remember what that meant in our previous one? That meant that even though it looked like a 2, it was really a 1 that was participating in 2 of our doublets. Or last time it was 2 of our triplets, but here it's 2 doublets. So this 2 is really a 1. I'm just going to make a note of that. That's really a 1 that's just overlapping with 2 different doublets. So that is a doublet of 2, and then that is a doublet of 2. All right? So we have to be careful, okay? Even though it might not look like a doublet, check that it's not really 2 doublets that are overlapping. Okay? So then our next, and you see it's 2494 to 2497. So that's not a doublet. That's not a doublet of 2 anyway. So our next signal pair is a doublet of 2. That's 1-to-1 here, 2497 and 2499. We have 2500 to 2501. We have 2505 to 2507. But that's 1 to 2. But the 2507 is also a doublet with the 2509. So that 2 again is also really a 1. It appears as a 2 because it's 2 doublets overlapping. 2 1s that are overlapping. Okay, so we'll treat it as a 1. So that's a doublet, and that's a doublet. Okay, and then at the very end here we have 2517. So that's a doublet. Okay, all the other interactions aren't 2 hertz, right? This was 6 hertz. Okay, this was 3 hertz. See that? This was 1 hertz. So we ignored them because our instructions were, the first pair said, look for a doublet, look for doublets that are separated by 2. Okay. So we found all those. So what are our midpoints? Because remember, we want to unsplit those. So our 2482 and 2484, they are centered at 2483. Our 2490 and 2492, that's centered at 2491. And these are centered at 2493. Okay. The 2497 and 2499, those are centered at 2498. And our next are centered at 2501. We have 2507 and 2505 and 2507 So that's 2506. We have 2507 and 2509, so that's 2508. And then 2517, or 15 and 17, that's obviously 2516. Okay. And notice that since we were able to disentangle a couple of these doublets and find that they were overlapping, everything is really a 1. So we're going to treat these all as 1s. The resulting centers are also 1s. So that's a 1, that's a 1, that's a 1, okay, etc. I'm not going to write them in. We can recognize that they're all 1s. So now what's our next pair? By the way, our first splitting that we disentangled was a doublet with a separation of 2. That's the first thing we did. So now what do our peaks say? Well, everything are 1s, so we have doublets all over the place here. Everything left is doublets. And our separation is 8. Okay, that pair are the top 2 numbers in our list are now 1 to 1, and they are separated by 8. So let's find all 1 to 1 separations of 8. So 2483 to 2491, that's 8. 2491 to 2493, that's not 8, so we ignore that. 2493 to 2498 is not 8. But 2493 to 2501, that is 8. Okay, so let me do it this way. So that was 8. 2483 to 2491 was 8. 2493 to 2501 was 8. Well, what about this 2498? 2498 to 2506 is 8. Okay. Right, 2501 to 2506 is not, that's 5. 2506 to 2508 is 2, that's not 8. But 2508 to 2516, that is 8. Okay. So we have 4 doublets here that are separated by 8. Again, and we knew to look for 8 because the first pair was separated by 8. So what's our new center? Well, if they're separated by 8, the center here is 2483. That would be to 2487, right? Add 4 basically. So that is centered at 2487. This is centered at 2497, right? This is centered at 2504. And this is centered at 2512. So we've now unsplit doublets of 8. All right. Let's keep going. Okay. Remember, these were all 1s. So we continue looking for 1-to-1 relationships. Everything we have are 1-to-1 relationships. So what do we have now? Well, the 2487 to 2497, that's the 2487 was a 1, the 2497 was a 1. So we're looking at 1-to-1, so another doublet. Doublet separated by 10 is what we're looking for. So these are a doublet separated by 10, and I'll just write that in here. We're splitting a doublet separated by 10. So 2487 is a doublet of 10. 2504, did I do something wrong here? I did. The center is not 2504 here. See, the fact that I was following a system, I caught my mistake. The center of 2498 and 2506 is not what I had. It is 2502. Okay. Right. Add 4. So 2498 plus 4 is 2502. Add another 4, you get 2506. So now we see that that's where our doublet is. 2502 to 2512. That's a doublet of 10. All right. So where are our centers? Well, it's easy. 2487, this to 2497. The center is at plus 5. So this comes to 2492. and this comes to 2507. Okay, so two signals, they all came from ones, so they also are ones. So we have a 1 to 1. And what is their separation? Their separation is 15. Okay, so the center, okay, is, well, they were at 0.5 originally. Remember, we removed all the 0.5s. But the center would be 2492 plus 7.5. So 24 is about 2500 again, is where we're centered. All right, so this is a doublet of doublets of doublets of doublets. We have 4 doublet interactions going on here. So think about what that means in terms of the structure. Okay, it's a single it's a single type of proton that has 4 neighbors. There are 4 single neighbors, and the relationship from that hydrogen is different to all of its neighbors. So it's like the hydrogen to a red neighbor, a hydrogen to an orange neighbor, a hydrogen to a green neighbor, and a hydrogen to a blue neighbor. 4 neighbors, and the relationship is different to each of them. That would give you a doublet of doublets of doublets of doublets. Something like this almost always arises from stereochemistry, either through a chiral center or 2 chiral centers or a double bond in there somewhere, where you have cis and trans relationships. That's usually where you get these very complicated splittings. So we have a wide doublet of 15, then a more narrow doublet of 10, then a more narrow doublet of 8, and then a more narrow doublet of 2. So that is what you see here. And would you have known that just by looking at the shape? No, you wouldn't have. Okay, at least I don't think so. I would not have. I would not have looked at that shape and thought, oh, that's a doublet of doublets of doublets of doublets. But by disentangling the numbers, you can solve that. So what does that splitting look like? It looked like this. So here I went back to our multiplet simulator, and I put in a doublet of 15, a doublet of 10, a doublet of 8, and a doublet of 2. You can see it's the shape is the same as what we were just looking at. I'll just compare that to that. They're really similar. The separation might be a little bit better in the simulator, but regardless, and you can see that tree at the top, okay, that hierarchy. Our center signal, again, centered at 2500. Then we have the wide doublet first. So we split our original signal into 2 new signals. That's our doublet of 15. Those green signals are each split into their own doublet of 10. Those blue signals are each split into their doublets of 8. And you can see the overlap, right? Remember how we overlapped our doublets in that 3rd tier? If we go back and look here, right? Our blue, okay, we had overlapping doublets. So our 3rd, we work from the bottom, but we look at it from the top. So our 3rd tier from the top, the pink to green to blue, those were overlapping doublets in the middle. And we see that. That's what you end up with in our graph. That's in here. It's the pink tier, unfortunately. But that pink tier, those triplets or those doublets overlap. And then each of those pink doublets are then split into subsequently very small doublets that are separated by 2. And those are where you get our signals. And any place that you get overlap, we had the double height, right? That would be right here, where a pink split into a doublet and another pink split into a doublet, and those resulting doublets happen to share a single frequency. So that's why you have 2 in our integration originally, and that's why our peak height is 2. So wherever we ended up with overlap, that's where we had a 2. Okay, these middles are only separated by 1 hertz, right? If you go back and look at our original list, here we had 2499 and 2500. Right? Those signals are almost right on top of each other. That's these. Okay. So this is the answer, right? But we solved it by working from the bottom up. We found the first splitting, then the second splitting, then the third splitting, then the fourth splitting. And I think you can solve, if you can solve multiplets like this, if you could go back and do this on your own, kind of looking out for the things that we learned to look out for, then I think you can probably disentangle any multiplet because it's so systematic. You just do one step at a time. You look for your first splitting, you unsplit all of those. You look for what's next, you unsplit all of those. You look for what's next, you unsplit all of those, and you keep going until you get back to one peak. All right, hopefully that was helpful. Just to kind of tie this back to where we started, if we had the frequencies for this peak here, hopefully we would be able to find that indeed it is a doublet of triplets. Okay, we'd be able to work out that same process and find that we have a doublet that's very wide, and then that doublet splits into subsequent triplets that are more narrow. And because first of all, that's what our structure says it should be. A doublet of 12 and then a triplet of 7. But if we had the frequencies, it would be nice to be able to see that. But in a real life situation, you'd have access to those numbers. If you were to go walk into a spec lab and take an NMR spectrum, the printout of your spectrum would have all of the frequencies, and you could go through this process and do that. All right, that is all. Hopefully this was helpful. Leave a comment if you have any comments or questions, and I will see you next time.